Welcome to The Explainer. Today, we're setting up the absolute ultimate heavyweight battle in system architecture. We're talking academic database theory going head-to-head against pragmatic internet-scale engineering. We're diving into distributed transactions, specifically two-phase commit versus the saga pattern. If you've ever wondered how tech giants like Amazon or Netflix manage literally millions of complex orders without their systems crashing into just a tangled mess of locked data, well, you're in exactly the right place. So let's dive right into this.
Okay, here's a quick look at our scale-up journey today. We'll start with the single database era, look at the distributed data problem, dive into two-phase commit, and then enter the saga pattern. We'll wrap up with choreography versus orchestration, and finally, building for real scale.
Starting off with Section 1, the single database era. Yes, the golden age of easy rollbacks.
Think of this as the much simpler times of your application's lifecycle. To really ground this, let's use a classic e-commerce analogy. When you place an order, the system has to do three things, right? Charge the credit card, reserve the inventory, and log a ledger entry for accounting. In this era, all of that happens seamlessly in one place. And the reason it's so seamless is because of ACID guarantees. Behind the scenes, your single database provides atomicity and isolation. Atomicity just means either all three of those steps happen totally together or none of them do. There's zero chance of a nightmare scenario where a customer gets charged but the item isn't reserved. And isolation? That means while this whole process is happening, no other part of the system can sneak a peek and see a half-finished order. The database handles all the heavy lifting, so developers just write their SQL and call it a day. It's safe, it's reliable, and honestly, it's practically invisible.
But of course, success brings traffic, and traffic brings massive amounts of data. Eventually, your application scales, your monolithic database starts hitting a wall, and you're forced to break it apart into microservices. Which brings us to the inciting incident of today's story. What happens when one database becomes three?
That leads us to Section 2, the distributed data problem. Subtitle, When Atomicity Breaks Down.
Suddenly, your payment, inventory, and ledger data live on completely independent machines. They literally do not know about each other. That simple, beautiful single transaction we just talked about, it's morphed into a distributed nightmare. This breakdown illustrates the contrast perfectly. Just look at the monolith side. Single, logical operations, automatic rollbacks, super easy. Now look over at the microservices side. Because a card charge is committed to a separate database on a separate machine, if the inventory reservation fails a second later, there's no automatic database-level rollback to save you. In a distributed infrastructure that's processing, say, thousands of transactions a second, partial failures aren't edge cases, they are just routine. Suddenly, you're the one who has to figure out how to manually clean up the mess across all these different systems.
So, how do we fix it? Section 3, two-phase commit, or 2PC. This is the classic textbook academic solution.
To fix this whole lack of coordination, 2PC introduces a central coordinator. Its sole job is to ensure every single participant in a transaction agrees on the outcome before anything becomes permanent. Here's how it plays out. In Phase 1, the prepare phase, the coordinator asks all the separate databases, hey, can you commit? Each database does the work, durably records the changes, and this is absolutely crucial, locks the affected rows so nothing else can touch them. Then they vote yes or no. Moving to Phase 2, if everyone voted yes, the coordinator says commit and all those locks are released. But if even one database votes no, the coordinator triggers a system-wide abort. On paper, it's a beautiful thing. It gives you the exact same strong consistency you had back with your single database.
But wait, here is the fatal flaw. 2PC is a blocking protocol. Imagine the coordinator collects all the yes votes and then crashes right before sending that final commit command. Your databases are now stuck literally holding locks on their data, waiting for instructions that are never, ever coming. Or think about a slow participant. If your ledger service takes 10 whole seconds to respond, or your payment and inventory services are completely frozen for 10 seconds, doing absolutely nothing but holding locks, your entire system only moves as fast as its slowest component. As the legendary software architect Pat Helland famously noted, distributed transactions across autonomous services don't work at internet scale. And this is exactly why you almost never see 2PC used across independent microservices. Sure, you might see it inside tightly coupled distributed databases like Google Spanner, where the system handles all that complexity internally. But for autonomous services that have their own deployments and their own failure rates, it's a recipe for a total system freeze.
Let's see what the industry actually uses instead. Section 4. Enter the saga pattern, the real industry standard for microservices.
When companies like Uber, Netflix, Amazon, or DoorDash need to coordinate work across microservices, sagas are what they reach for. But it requires a fundamental shift in how you think. You have to completely abandon the idea of strong, all-or-nothing atomicity. Instead, you break the distributed transaction into a chain of independent local transactions. Each service does its own work and commits to its own database immediately. There's no waiting, no long-held locks across the network. What you get instead is called eventual consistency. The system might briefly be in a slightly inconsistent state, but it never blocks, and it always converges to the correct state eventually.
Now, you might be wondering, if services commit immediately, what happens when a downstream step fails? That is exactly where the compensating action comes in. Because you can't rely on those magic database-level rollbacks anymore, you have to build explicit, business-level undos. If a card was charged, but the inventory turned out to be out of stock, your compensating action isn't a database rollback. It's triggering an actual API call to issue a refund. You are explicitly building logic to detect failures and clean up the mess yourself.
Which brings us to Section 5, Choreography versus Orchestration. 2 ways to manage the chaos.
If we have a chain of local transactions and a whole bunch of compensating actions, how do we trigger them and keep track of everything? Well, what's really interesting here is seeing how engineering teams naturally mature. On the left, choreography is decentralized. Services publish events like card charged, and other services just listen and react. It's fantastic for simple 2 to 3 step flows. But once you have 5 or 6 services all reacting to each other, debugging a failure means digging through logs across a dozen different systems. It's a headache. That's why teams almost always graduate to orchestration at scale. You introduce a dedicated orchestrator using tools like Temporal or AWS step functions that actually commands each step and knows exactly where a transaction is stuck and exactly which compensating actions to run.
However, we can't just pretend orchestration makes everything perfect. The reality is, compensating actions are messy. Think about it. A database rollback is invisible, but a Saga compensation happens in the real world. A customer might actually see a charge and then a refund on their bank statement. If a step involves sending a confirmation email, you can't magically unsend it. And because compensations themselves can fail, what if the refund API is down? You need some serious reliability engineering. Your retry logic has to be strictly idempotent. That means you could retry a refund 10 times without accidentally refunding the customer twice.
And that brings us to the final boss of Saga architecture, Section 6, Building for Real Scale, Solving the Dual Write Problem.
Okay, picture this. Let's say your card service successfully charges a card and updates its local database. Now, it needs to publish an event to the message broker so the next service knows to proceed. These are 2 completely separate writes to 2 completely separate systems. If the database write succeeds but the network blips and the event fails to publish, your entire saga just stalls forever. Or even worse, the event publishes, but the database write fails, meaning your downstream services are now reacting to a phantom event that doesn't exist in your database. That's the dual write problem.
The truly elegant solution to this is the transactional outbox pattern. Instead of writing to the database and publishing to the broker as 2 separate, risky steps, you do this. Step 1, use a single local transaction to write your business data and write the outgoing event to a special outbox table living right there in the exact same database. Because it's one database, they either both commit or neither do. No phantom events. Then, step 2, a separate background process reliably reads that outbox table and pushes those events over to your message broker. It effectively keeps your events exactly as reliable as your data. It's brilliant. But before we wrap up, we absolutely need to talk about the golden rule, the single best way to handle a distributed transaction. So the crucial point here is this. If you can design your service boundaries so that data that needs to transact together lives in the same database, just do that. Seriously. Before you reach for complex sagas, outbox patterns, and orchestrators, ask yourself, can we just merge the inventory and payments tables into the same database? Because avoiding a distributed transaction altogether is always the best architecture.
But hey, when you can't merge them, the Saga pattern is the undisputed standard. Accepting eventual consistency is a deliberate trade-off the industry has made to achieve infinite scale. Yes, you lose the comfort of ACID guarantees, but you gain a system that never blocks and can scale endlessly. So I'll leave you with this provocative thought. As you design your next system, are you ready to let go of your comforting database locks and embrace the messy, eventually consistent reality of building like Netflix and Amazon? Thank you for exploring this with me today on The Explainer. I hope this really clarified things for you. See you next time.